because, as I had said, 3.5 is how to graph rational equations or rational functions. All right. And it's sometimes hard to figure out. And I'll just show you what I'm talking about. Let's see if I can find a good one and I'll show you. No, I'll just make one up. Oops. All right, so probably most people here know about, but when you get into other ones, and this is what we call a rational expression because of the fact that it has it's fraction essentially, bar, and you notice that it's kind of a little hairy to think about graphing something like this, but in Math 130 they go through this, and basically what you do, you find your x and y intercepts the same way you would for any other equation or function. These things in the bottom, that's where the function is undefined. X can't be -2, and so you'll see it may be hard to see, but at -2 this thing's never touching -2. It gets very close to it, but never actually gets there. The same thing with 4, x is equal to 4. It's never going to get there. So those are what they call x asymptotes. In other words, they're values that the function gets very close to, but never touches. All right. And they also have this thing called the y asymptote. In this case, the y asymptote is 0. And then you look for things like symmetry, and you look for shift, and all those type of things. Because we talked a little bit about transformations, and this x minus 3 means that it shifted 3 to the left. All right, if that was just an x up there, let me show you how it would change. See, it would just shift. Okay, so what 2.6 does is it tells us a little bit more about how to graph, and I'm assuming that that can play with 2.5 and also tell you about graphing things. But anyway, let's just go through this little PowerPoint, and then I'll do some problems to show you some things. All right, now first thing is to talk about polynomial inequalities. And a polynomial is just basically a function where you got a less than, a greater than, a less than, equal to, or greater than or equal to. Okay, and we mean by polynomial, you got more than one term, and you could have x cubed, x squared, x to the fourth, those type of things. Now, in order to solve an inequality, you've got to have the inequality in a form very much like a quadratic. When you solve it, you have 0 on one side and you have your function on the other. In this case, it's not equal to, but what we'll do is we'll use the point. We'll use the equation to find these things called boundary points. And then that'll tell us where we're going to check things at. And when I say check things, we're going to find some information about this, and we want to establish these boundary points and check things in between them. And then, like any other inequality, or like we've done with other things, we'll then we'll then be able to find out what's part of the solution for these inequalities. All right, so let's go on. And then once we have these boundary points, it's going to make at least two different segments of the graph, because if you have one boundary point, there's half on the one side and another half on the other side. And if you have more than one, I'm sorry, more than, one and two or three, it's going to create several little segments, and that we need to check. Now, essentially, you just put a value into the original inequality, and if it comes out true, then that's going to be part of the solution. And if it comes out false, then that's not. But the way this book handles it's a little bit different. In other words, they just look to whether it's positive or negative. If it's positive, it's part of the solution. And if it's negative, it's not. And then you write the solution set with interval notation. So no matter what sign you have, you still work with the boundary points with the equation, right? And then you can compensate for whether it's less than or greater than or the equal to in there. All right, so here we got a polynomial inequality. X squared minus 2 is greater than 20. And we have to have 0 on one side. So we're just going to subtract the 20. And then we've got something that we can work with. Well, what we're going to do is just play like it's an equation and solve it. And that's factors as x minus 5, x plus 4. So x is equal to 5, x is equal to negative 4. So those are boundary points. What do I mean by boundary points? Well, see, negative 4 and 5. So they make a little dot here. You could make a line. It doesn't matter what you're looking at, because you don't know yet whether we're going to include that value or not. It's just that's where we're going to check one over here, one in this one, and one on the other, because the two boundary points create three separate segments. And that's how they've got it divided up. Negative infinity to 4, negative infinity to negative 4, negative 4 to 5, and 5 to infinity. And the reason why they use the parentheses, okay, and not the equal sign, is just because there was no equal sign on that thing. All right. So in this first one over here, we could check anything over here. Negative 5 seems the most obvious. Use whole numbers. You don't have, if you pick fractions, it's going to make your life harder. But just know what's over there and use it. It doesn't matter which one you use. So we're going to go left to right. So negative 5 is the obvious one to check, or the closest one to check. So we just put it into the original x squared minus x minus 20. So negative 5 squared is 25, plus 5 gives us 30, and 30 minus 20 is 10. And since that's positive, or essentially makes this statement true. In other words, hold on a second. Yeah, because 10 is greater than 0 once we put it in there. Anyway, you know what? This is messed up. I'm just now noticing that. There should be an X there. I don't have the way to edit it, but that should be. That should be an X, not a 2. So just realize that This is what it should be on the left, and then the 20 was over there to start with. All right. So this positive, or it was true with the original inequality. So what we can conclude then is that between negative infinity and negative 4, that's part of our solution because we just found it's greater than. Now, this is going to connect to something a little bit more interesting in a bit, okay, about what this means. But that's part of the solution right there. But we're not finished because we've got one in the middle between negative 4 and 5. 0 is smack in there. 0 and 1 are your friends if you can use them. So we're going to put 0 in there. And we would come out with negative 20, which is negative, and it will also have the property that it would be false if we have a negative 20, because negative 20 is not greater than 0. But you can still deal with it in this sense, the way the book talks about it, that it's negative. So this thing, for all that range right there, that's not part of the test solution. I mean, test thing. So we just know that it's less than, and I'll show you in a minute what it means. All right, and then the last one was something greater than 5, and they just use 6. Try to keep it as simple as you can. Like I said, avoid using fractions if you can. And like I said, is always pick something not on the line, but above the line or below the line, or below the point, I should be saying, the boundary points. All right, so we put 6 in there. 6 squared minus 6. So let's see, 6 squared is 36. Minus 6 will give us 30. 30 minus 20 is 10. It's positive. So what we can conclude is that anything in that range is going to be greater than 0. All right. Another way of looking at it is all of those things are in the solution set for from 5 parentheses over to infinity. So this is the way that solution set looks. In we've already in the interval notation that it's negative infinity to 4 union infinity. The way the graph looks is like this. So this is part of the solution, and this is not part of the solution. And everything is part of the solution. So I'll show you something. Let's see, what was it? It was that's it. Okay. Now, this is a polynomial, and like I said, is some of these polynomials can get really big. All right. There's something wrong. Something doesn't seem right. Well, I'm just going to blow it up just so you can see, because you can see it way down here. The reason what it does, it kind of steals the, takes the, just kind of by default, since this is an infinite solution, it's going up and up and up. They just keep on going and they make the scale, but we don't need all that. I just want to make sure that this was the right one. All right. So let me just show you what this means kind of in respect to the graph of that function, the one that we solved. All right. Now, Here's the -4. And the other one was 5 comma 0. All right, so we checked from here on back to the left. We checked in here, and then we checked over here. Now, just kind of quizzing you a little bit, just to wake up your brain to see if you see this. What do you notice about the similarities between the graph and this interval notation? It's really pretty simple, but it might not be that easy to see just because if it's your first time seeing it. All right. Notice that from negative infinity, which is all the way out here, up to -4, y, or the functional value, is what? It's above the x-axis, so it's positive. Well, when we tested that point, what was it? Was it -5 or -5? See, we tested right here, and it told us that value was 5. And I think we came out with, what was it? Yeah, we came out with 10. So that was correct. But what that showed us, because it was positive, it means that that part of the graph is above the x-axis. The one we checked, when we checked 0 and it came out negative, well, that was good information. It was true. Notice that the functional value for everything between -4 and 5 is negative. It's below the x-axis. The y value is negative. Okay. And then on the other side was 5 to infinity, all the way out there. This assures us that everything is going to be above the x-axis. The y values, or the functional values, are going to be positive. So what this can be used for, like I said, we didn't really cover 2.5, but if you did, that would be something to assist in helping you know how to graph it, because sometimes it's hard to know, what the graph looks like. And this can help you do that. All right, any questions at all? All right, now just a heads up, I've probably mentioned this, but I'm not sure how much I emphasize it. Your inequality, well, it was the same thing with the polynomial. It had to be set equal to 0, or set greater than or less than, or whatever your inequality was in 0. That's the only way it works. So likewise, with a rational inequality, which is one like I first graphed, it's going to be the same situation. So if it's not set 0 on one side, or if it doesn't have 0 on one side, we got to fiddle with it, and sometimes it takes a little bit of work to do that, but not that much work. Okay, we've got that top one right there. It says solve and graph the solution set of 2x over x plus 1 is greater than or equal to 1. Well, the problem with this one, we cannot proceed, is because it's got a 1 over there on the right, not a 0. So we've got to fix that. And how are we going to fix it? Well, first of all, we're going to do just the same kind of thing we do with the equations. We're going to subtract 1. subtract 1. So we got 2x over x plus 1 minus 1 is greater than or equal to 0. But we need to have a single rational expression on the other side. And there's a reason for that. So if you don't understand anything about this process, I'm going to go through it because I'm assuming people understand common denominators, but I don't have any problem going back because fractions are hard to understand, you know. All right. So we're right here at this point. So this is not one single rational expression. It's two terms. So what we got to do is we got to give this one the same denominator of x plus 1 that this one has. All right. So just to kind of show you in a very basic example, let's just say, go back, harken back to the days of when we were just looking at normal fractions instead of the ones that's got x's in it and such. All right, let's just say we have okay, 3/4 minus 1. All right. Now, if we were told to add or subtract, which in this case is subtract, we need to have a common denominator. We can't do it. So what's the LCD on this? And if you're having trouble visualizing it, keep in mind that this is 1 over 1. All right. So the LCD between these two is what? 1 can fit into 4, but 4 can't fit into 1. So the LCD is 4. Okay. So what that entails is we got to fiddle with this to make sure that it has the same LCD. And this procedure is as old as the hills because in order to create a common denominator, you got to multiply numerator and denominator by the missing factor, which in the case of our right-hand friend is 4. So what does that come out to? Well, 3/4 doesn't change. And then 1 times 4 is 4. 1 times 4 is 4. Now you'll see they both have the exact same denominator. So what can we do? Once they got the same denominator, you just do whatever operation is up there. It's 3 minus 4 is negative 1/4. All right. I'm going to go through that because that's what's happening over here. So make sure you understand it. All right. So the way that they make this negative 1 have the same denominator is they multiply by that LCD, which in this case was x plus 1. X plus 1. So both the numerator and the denominator, although they're not showing you the 1 over 1 like I was, is just basically you're ending up with 2x minus x plus 1 right there over the common denominator of x plus 1. Now remember when we subtract, we got to run that negative sign through everything there. So that's negative x and negative 1. And then we can simplify these. 2x minus x is x. And then we've got minus 1 over x plus 1. All right. Now that we got it like that, where we got just one single solitary term. Now, in the case of the inequality that we looked at first with the x squared, there was no way to make it one term. But with a rational expression, it's very important to do that. And we should always be able to do that. And there's a reason behind it. And I'm going to show you because you need to know what values make this thing undefined. All right. And as you remember, Okay, this telling them that this is equivalent to that. So it's in the form of the function is greater than or equal to 0, and it's just x minus 1 over x plus 1. Now, what this tells us is if we take that x plus 1 and solve it, well, I'll tell you what, they do both the numerator and the denominator, and there's a reason for that. I'll explain in a minute. But this one right here, we'll look at that one first. The x plus 1 is equal to 0 means x can't be equal to negative 1, because if x is equal to negative 1, we got a problem because it's an undefined expression. So x is equal to negative 1, it can never equal to that. So just remember that when we make up our solution set. But we also do the numerator, and the numerator is not an undefined value. It's just what we call a boundary point as well. Both of these are boundary points, but on this one, it's just the numerator. So x is equal to 1. So 1 and negative 1, or negative 1, 1 are our boundary points. All right. So we mark them on there. And like I said, in a way, it's kind of a bad idea to do it with a circle just because, I mean, a dot, because for some people back in high school days, and even in the early, like Math 097, they kind of know that a lot of people have done the open circle and the filled in circle to be meaning that it doesn't include the number, and where it's filled in, it includes the number. So that's kind of what bothers me about this. But all we're doing is just we're looking at this segment, and this segment. So we can pick anything in here for one test. We can pick anything in here for a second test. And we can pick anything over here for a third test. All right. So the first thing they do is just go right next door to negative 2. And then they're going to put it into this inequality. And when you do that, you got a negative 2 up there, minus negative 1, you can make it negative 3. Down here, it's negative 2 plus 1, so it's going to be negative 1. So negative 3 over a negative 1 is equal to 3. All right. So since that's positive, then we can conclude that that whole range now is going to be the same. From negative infinity to negative 1, not including negative 1, is going to be positive. And I'll show you a graph in a minute, and I'm going to see what you remember. Now, the next one was 0. Because that was smack dab in the middle. You could take 1/2 if you want to, or negative 1/2, but why torture yourself? Pick 0. 0 is your friend, because it means that you got a lot less math to do. So 0 minus 1 is negative 1. 0 plus 1 is just 1. So it's negative. So therefore, everything in that range is everything from negative 1 to 1 is not going to be in the solution set because it's negative. All right, y'all follow me? All right, look at the next one. Take a gander. All right. So using 2, which like I said is that was just another value over there, and so you can just use the next one. You could use anything. 3, 4, 5, all the way up to a billion if you wanted to. But the smart move is just always take the easiest when it's going to give you the easiest calculation. So f of 2 is 2 minus 1 is 1. 2 plus 1 is 3. So 1/3 is positive. So everything in that range there on the right is going to be positive. All right. All right. So that means then our solution set is going to look like this. Over here is part of the solution set. And everything over here is part of the solution set. Now, because that one was in the numerator and it does not hurt it to be that actual value, if you remember. See up here, if we put 1 over there, we'll have 0, but it won't be, there's no danger to it collapsing because of being undefined like it would be if it was in the denominator, a -1. So that's why they use a bracket there. All right. This right here is what we call set builder notation. Um, you might see some things displayed in that and just realize it means the same thing. X is less. This right here is just kind of to set it up. It's all the same. It means X such that X is less than -1 or X is greater than or equal to 1. So there's your solution set. All right. Any questions? I'm going to find a couple out of the book and go through those, but I wanted to see if y'all have any questions. We've got plenty of time, believe me, so don't feel bad about asking anything. I really try to time the course so that we have plenty of times. Every once in a while, if we lose some days or something, I might be in a rush, but we just got this to finish today and then we're ready for our, oh, and that's a good thing to reiterate because I noticed people came in late. I don't know why it keeps going down to, it's resetting or something. All right, so we're right here on 1026. So we're covering the 3.6 polynomial and rational inequalities. And then Thursday, we're open for review the whole day. Bring any questions you got. If not, I'll just go through that practice. But and then the test will be open and probably like until Monday or something. But we'll talk about that Thursday. All right. So y'all still with me? All right, I'm gonna find us a problem here from the textbook. This is 3.6, right? The rational ones are the harder ones to do, but that's why I kind of like to concentrate on those. All right. All right. So let's look at this one. This one's not going to take. All right. This one is not going to take having to change it. We'll look at another one of those in a minute. But anyway, what we got to do is we got to work with this thing here. All right. Look at it as a function for a minute that's set equal to 0. All right. So what we got to do is when we got a rational inequality, we got to solve the numerator and denominator to get those boundary points. So first, all right, so this one's going to be x minus 3, x plus 3 is equal to 0, which means x is equal to 3. And x is equal to negative 3. And then over here, anytime you got a variable set equal to 0, it's going to be 0. So, all right, so here's 3 boundary points, okay? So it's hard to make a line with this system because they don't really have a line. They really need one. Oh, maybe this will work. Nah, it just wants to be an arrow. Anyway, let's go back to the black and I'll draw one. All right, so we got negative 3, we got 0, and we got 3. All right, now, so we're going to check, let's just say we'll check negative 4, negative 1, and 1. Whoops, whoops, whoops. Wait a minute, wait a minute. Oh, no, 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 no. Yeah, that's right. 1, and then we got the other one. Whoops, put 4. Make sure I got that right. So we got this little section. We got everything from negative 1. So in other words, this is negative infinity to negative 3. This one is negative 3 to 0. And then this one is 0 to 3. And then this one is 3 to infinity. All right, so we need a new page. I have to go back. Let's say we want x is equal to -4. And it was 4, wasn't it? Double check. Okay. So let's just check everything and back in the original. Um, and we'll just do it as an equation, okay? As a function. Okay, so that's going to be -4 squared is 16. 4 times 16 is 64. Down here it's 16 minus 9, which is 64 over 7, right? All right. Since that's positive, greater than 0, this is the one we want to remember. Okay. Since it's positive, that's the one we want to remember. Let's try f of -1. I hope I got enough room to squeeze them in here. So with the numerator, it's just 4. Down here, it's going to be 1 minus 9. So that's negative 4/8, which is -1/2, which is less than 0. So this one right here, I'm going to write it, but we're not going to use it. Okay. And it was to 0, right? Yeah. But this is part of the solution there, not this one. And usually they're going to alternate, but not always. There's probably a rare one that won't alternate. So this one didn't. So I'm expecting that this one will be positive. Oops. And that's just 1 minus 9. So that's still going to be 8 negative. So this time we got -1/2. Hold on a second. Did I do something wrong? So in the numerator, it's 4 times 1, 4. And it's 1 squared minus 9, which is 1. Hold on a second. Did I mess something up? No. So here's going to be all right. So this is just going to be less than 0. So then we can rule this one out. This one's 0 to 4. Here I was thinking that most all of them, just got to finish saying that most all of them are going to be on off, but it's not necessarily. Because I had another one that I was working on, and I just that had like two falses in a row, and I said, well, I thought this one wouldn't be like that, but it doesn't hurt it. So this is going to be an awful lot like the last one. It's going to be the exact same value because 16 minus 9 is 7. So it's greater than 0. So then this one is 0. I'm sorry, 4 to infinity. So here's our solution set, we call it. Okay. This one second. I want to find. It's going to be right back. Okay. All right. So now this is our solution set. Okay, that's what they want in 2.6. But I want to relate this back to 2.5, just so hopefully you can see this pattern here. Well, let's start another graph. Oops. All right, so this is what this looks like. Really pretty weird. All right, so it's kind of hard to see. Let's see. But right here is x is equal to -3. So let's see, x. Okay. Let's see if I can get a different color. Sorry about that. Is this little Chrome box I use for my audio and video? I don't know what's going on with it. I tried replacing memory. I thought maybe that's what it is. It's just like it gets to a certain point and then it just freezes up. So I don't know why it does that. I replaced memory in it and that didn't do any good. All right, y'all still hearing me okay? All right. So anyway, back to this. So between -3 and 3, notice that everything's below the x-axis. Okay? Well, that's what this is telling us. Anything we picked down here was negative, so we know that the graph of that is going to be below that x-axis. So that's why this is important for another reason, just because when you're solving something as an application wise, you usually have a graph associated with it and the graph can explain things. It's just like we maximized or minimized values in the quadratics section or the quadratics chapter. And the vertex helps us find that because if it's parabola like this one, then that's going to be a max. If it's turned the other way, then it's a minimum. So it helps to be able to look at the graph and know why that solution works or why that method works. All right, so let's just look at the application here and then we'll be pretty much done. All right, so this looks mean, but it's really that not. It's just what we call, this is actually just a parabola. Okay, and I'm showing you the graph in order to try to take some of the mystery out of it. Hold on a second. We don't have the values yet. All right, so they just give us a kind of a generic equation. It's got -16 t squared, and t is time, and the s of t, which has to do with it just it's called the position function. It's where it's at a specific time. This thing right here, these parabolas that are negative like that on the x term thing, they're very handy for anything where you're dealing with things going up in the air, because things are going to go up in the air. Like if they're shot up in the air, they're going to make an arc and come back down. They'll reach a maximum. But anyway, that's just a generic one. And then they're going to give us one that's specific. All right. An object is propelled straight up from the ground level with an initial velocity of 80 feet per second. All right. 80 feet per second. So this right here represents a velocity. Its height at time t can be modeled as such. Again, the s of t refers to the position that this thing is in, okay, at any time t, and it's seconds. In which time interval will the object be more than 64 feet above the ground? All right. So first of all, they're going to put everything on one side. But again, I'm going to graph it just to show you what we're going to be dealing with and why we're solving this. Did it make it? Or is it just huge? Well, what am I missing? thought maybe it's just way out, but something's not right. I'll tell you what. I'll tell you what. I'm just going to use X. Maybe that's what it doesn't like. Okay, there. And then when I put T, see, it goes away. It likes X. Okay. And then it was plus 80T minus 64. Oh, and I went back to T, and I got to have this X. All right. So the way it looks, and you can't tell that it's a parabola because it's so thin. But if we go in and looking at this graph, like I said, the scale is way out of whack. So once you zoom in and see, you'll see where that it's above that axis right there, okay? So if we do the calculations like we've been doing, it should tell us everything from 1 to 4. But let's go ahead and look. So first of all, we write it with everything on one side. Then we did set it as equation and solve. In other words, we're factoring x minus 1. Now what they do first, and this is always a smart idea, factor out the negative if there's a GCF. Always if there's a GCF, you should factor it out, especially if it's negative, because if you end up with a t squared that's negative, well, don't come to me about how to factor it. I have to factor that negative sign out because I like dealing with a positive t squared. All right, and so t squared minus 5t plus 4 factors as t minus 1, t minus 4. So t minus 1 is equal to 0. So t is equal to 1. T minus 4 is equal to 0. So t is equal to 4. So we got two boundary points. All right. So the boundary points were 1 and 4. And then we're going to check 1 over here. And remember, I'm betting that this is going to be negative. So let's use a calculator here and do it. Oh, I know what I can do. Actually, this is kind of neat. I mean, this Desmos thing, it actually lets you do calculations. So I'm just going to type it in there because they don't show us. So from 0 to 1, well, you're going to do 1/2. It's got to be a fraction. So let's just say all right, comes out to negative 28. So as I said is, this one right here is not in the solution. All right, let's just check one over here. I'm going to just copy and paste that and replace it with something. What do I want to replace it with? Let's replace it with 5. So this comes out to negative 64. So again, it's negative, so does not produce any positive value. So it's not above the line. All right. But if we check something in here and we can just easily check 2, bet your bottom dollar that this is going to be positive. Now, you don't really have to go through, see, it's 32, positive. So that tells us that that's where it's above the line, in between 1 and 4 is above the line. And like I said, I'll re-graph it here with the axis. So again, see that? That's where it's above from 1 . Oops, it was 4. So see, that's what that's telling us, okay? Like I said, it's a simple way to deal with quadratics or any kind of function to solve things. And like I said, this is a perfect application. Well, I was going to try to go through another one if you want, but I'm not sure we have enough time. Anybody want me to go through another one real quick like that? I thought I had the darn. Oh, it's because I had to restart this crazy thing. I already had the book open. Actually, I didn't have to restart it. It turns itself off for some reason. All right. So anyway, Thursday, review. It keeps changing. So here we are right here. So Thursday we will review, okay? If you got any questions, stick around. I'm here. But just keep in mind, all of these applications are just going to be setting up a polynomial of some sort or rational expression and doing what we just did to it. If it says above, then that's what you use. If it's below, then you know it's the ones that come out negative.